class, that is half a dozen from Accentus, and it is related to the capacitance. The capacitance chapter for board already we have done. Just a few days back I had uploaded that particular video, and today we'll be dealing with problems which is actually dedicated towards the All India entrance examinations like JEE Mains, JEE Advanced, NEET, UG and other state level entrances. So here you know already that in this class we actually develop our concepts, because it is impossible to solve all the problems and prepare for the entrance exams. No, that is not the right approach. And the right approach is to understand the basic concepts of a particular section or a chapter, and then you can actually approach towards the solving methods of the given problem in the entrance examination or in this cluster. So what I suggest is, don't think about the formulae. Okay, for entrance always think about the right concept. Okay, not only the concept, the right concept you have to understand, that which concept you have to apply for solving this particular sum. Alright, so keep your classwork ready. I'll start with the problems. So here comes your first problem.
Here is the problem. It contains 4 metallic plates with a surface area of A and separation D, and plates are connected as shown in the figure. It's connected to positive A and B, two terminals, and we have to calculate the capacitance of the system between A and B. This is the problem. Please do copy this in your classwork and we'll solve this now.
So I hope already you have written the problem in your classwork. You have the picture, and now we are into the solving the problem. And here I have redrawn the circuit, whatever the diagram it was given in the sum. I have redrawn it, and here comes, I was telling you, think about the concept. Formula will come later. First you have to understand what is the concept you should apply. Okay. So here was the original diagram that they had given to us, and what you can see here that both the plates of a single capacitor, they are connected to two different terminals A and B. So this capacitor is basically this one. You can see here I have converted this one taken here to this, because you can understand that finally this is the capacitor which are both way connected to A and B like it is. Alright. Okay, so now there are two more capacitors here and here. Okay, and these two capacitors are finally connected to the external one, and finally they are going back to the the circuit from A to B. So it is taking one part which is directly connected to this capacitor, and these two capacitors are indirectly connected to the another part to B. So these two, I understand that these two capacitors are in series and this is in parallel. Okay, so this is the expression, these two are in series, and with that the middle one in the given diagram, which I have drawn it in the upper side, that will be in parallel. So obviously you can easily find out now that what is the equivalent capacitance of this arrangement. You need not to think. Okay, and it is equal to 3C by 2. If you apply, these two are in series, with that this is in parallel, so obviously these two will give you C by 2. This is series combination, and with that it is in parallel, so plus C again, so 3C by 2, and each of these capacitance, they are epsilon naught A by D. This is a parallel plate, so I can write this as this expression, that C equivalent here is 3 epsilon naught A by 2D. This is the final expression of this given problem. You see how much time actually we took to solve this problem is nothing. We just first thought about the situation. We just categorized that how we can transform this circuit into the simpler one, and then we can solve. Okay, if we cannot transform this circuit into this simple form, then we cannot do this calculation. So first we have to think that what concept we are going to apply, and again I am repeating the concept. The middle one, this capacitor is directly connected to A and B, directly connected to A and B. You can see this plate is directly connected, this plate is directly connected. These two, the upper one and the lowest one, they are indirectly, they have another loop through which they are connected to A and B. Because since these two are connected, so this will definitely induce charges. So this will be in the highest potential side, this will be in the lower potential side. So this way, A to B, we have two more capacitors, this one and this one, to be connected in series in the lower part. So this is simple, this we have had to think, and this we have thought about, and then we can apply these kind of concepts to solve the problem. Okay, so first we have to think about the concept. Let's check it out for the second one.
Is another one. It's an isolated parallel plate capacitor of capacitance C, and for surface they have charges like Q1, Q2, Q3 and Q4, which is shown in the figure, and we have to calculate the potential difference between the plates. There are 4 options given. This is very tricky one, very interesting one. Do copy this in your classwork and we'll solve it now.
Here comes the second problem, and I hope you have already written the problem in your classwork. The picture came up. Anyways, so they have given us a lot of charges between two parallel plates, and they have mentioned the capacitance is C. Okay. Now, in order to solve this problem, we have to actually understand. We have to fetch few concepts, few sections of capacitor as well as from electrostatics. First of all, let us imagine about Gauss's theorem, where we did the electric field in between two plane sheet of charge, where the surface charge densities were equal, sigma and minus sigma, basically, because positive and negative the inner plates are that way arranged. So now here, and that concept we already used in solving or deducing the expression for parallel plate capacitor. You remember E equals to sigma by epsilon naught. This expression we used in parallel plate capacitor, and these two concepts we have to jot down in order to solve this problem. Okay, so the outer plates, there are 4 charges, Q1, Q2, Q3, Q4 they are mentioned. But the outer plate charges are not that important, because capacitors, when it is formed, they actually store charges within the inner plate. The outer plates are usually earth, so that excess charge can flow, and all these concepts are there. So using all this, I have written already that Q2, the charge within the first inner plate, it should be equal to the opposite and same magnitude, where is equal to minus Q3. Q2 is equal to minus Q3. This is the key concept to solve this particular problem. Okay, now they asked us to find out the potential, and we know that the potential is total charge by total capacitance. They have mentioned the capacitance to be C here, and total charge here is Q2 by C, because the inner plate, and there's the minus Q3 here. Now we will do some arrangement. We will multiply 2 both in the numerator as well as in the denominator. Why? Because this will help us to find out the exact expression involving the exact charges within the inner plates of the capacitor, which are Q2 and Q3. Not only Q2 is within the inner charge, inner plate charge, the Q3 is also the inner plate charge, and we have to somehow formulate them into a single expression. This is what I am thinking right now. Please understand the concept. Don't follow the search for the formulae. Okay, first we have to search for the concept. Okay, right. So 2Q2 by 2C and 2Q2, I can write like this. Definitely, you agree to that. And from here, we can easily write the final expression, because minus Q2 is equal to Q3. So this is simply is this, and this is the expression that we wanted to find out for solving this kind of problem, and this is what we have done. You see, we again searched concepts from the sections we already did in capacitance, even in Gauss's theorem. Then only we can approach to this particular sum, and this concept, this particular situation is very important for solving other problems which usually comes in entrance. So this will help you to solve several other problems. Okay, now we'll go for the third one. Okay, so here is the problem number 3, which is very interesting again, as I am doing a lot of interesting problem in order to develop your concepts so that we can approach towards the problem. Here is the problem here. they have given us 5 plates, 1, 2, 3, 4, 5, okay, and they have given us that these 5 plates has been sorted. I mean, the connection is like 3 is connected directly to the battery, and 2 and 4 are sorted, and 1 and 5 are sorted, they are connected, and they have asked us to find out the charge here, that means plate number 1, and the charge on plate number 4. This is the question. Find the charge on plate 1 and plate 4. This is the question. So now this can be resolved. This is again redrawing the circuit. So I have resolved it already. So let us discuss how we can actually draw this pattern using the situation here. Again, we have to apply the concepts, how the plates are connected to other plates. That is very important here. Which side is positive, which side is negative, that is also very important. So first identify the plate number 1. You can see the plate number 1 is only connected to plate number 5. There is no other connection. So I have taken the plate 1 and 5, and they are connected to the same terminal. So here it is the terminal, and since we have an intersection, so it is towards the seat, this is always the positive one. Okay, and now on the negative side we have 2 plates, which is 2 and 4. So 2 and 4, they are common to a plate of 1. So 2 and 1, they will form one capacitor, which is this one. Okay, 2 and 3 will form another capacitor, where 3 is already connected, one side towards the negative terminal, another side towards the positive terminal. So this is how we can form here. So we can understand that 3 and 2 will form another capacitor. Then 3 and 4 is already connected to the negative side. So 3 and 4, they will also form another capacitor, and 4 is on the negative side. And finally the 4 and 5, 4 is always towards the negative, as I was telling you. 2 and 4, these 2 plates, they are connected to the negative. You can see this is the negative side, this is the positive side. These connection 2 and 4 is negative, 1 and 5 they are positive, and 3 is the source, so it will be always positive. So in this way I have arranged 1, 2 first capacitor, 3, 2 second capacitor, 3, 4 the third one, and 5, 4 the fourth one, and they are all connected to the potential V. So we have to calculate the charge on first capacitor and the fourth plates, sorry, not capacitor. So this we have to calculate now. Let us find out how we can do this. So what is the charge here? How we can calculate the charge? The charge here is all these plates, they have a plate area of capital A, separation is small d, and epsilon naught, these are air capacitors, so epsilon naught. So Q is equal to, the total charge is equal to CV, which is epsilon naught A by D into V. Okay, this is the expression for parallel plate capacitor. We know that epsilon naught A by D, and this is into V. The potential will give you the total charge. Okay, so first we want to calculate the first charge which is there. Now 1 is definitely positive, and what is the total capacitance? Epsilon naught A by D. What is the total potential? Is V. So what is the total charge? Is epsilon naught A by D into V. This is the charge on plate A. This is calculated. You see, I am applying concepts at the same very time. I am also thinking about the formula. Right concepts can only fetch right formula to solve. Okay, so here is the thing. Now we'll move into the other one, that is 4. We have already seen that 4 is connected to the negative side. In the diagram also it is mentioned. So the charge residing on 4 will be definitely negative. Okay, so how many plates are there? How many occurrence of 4s? 2. So total, each plate of 4 will definitely have this amount of charge, but in negative. So total charge on 4, on plate 4, total charge on plates 4, mark 4. There are 2 occurrences. Each is having epsilon naught A V by D. This is the charge they are having on 4. Potential is V. Total capacitance this forming 5 4 or 3 4. It is epsilon naught A by D. So obviously the total charge for each individual plate number 4 is epsilon naught A by D, but it is negative because these are connected to the negative section. Alright, so total charge will be twice of this, and this is the final answer, this one and this one. So I can jot down epsilon naught AB, I'm sorry, this is on plate 1, and minus 2 epsilon naught AB by D, this is on plate number 4. Two occurrences here. For one, it is only one. If we had occurrences twice, we would have multiplied it 2 or added them up because they are having the common potential. Okay, you see, so interesting it is, and we can approach in a right way. We have searched the proper concept and then we apply the formula, and here we have the expression for this particular thing. Okay, now we'll come up for the next one. I'll show you some concepts that are very important for circuit solving problems in capacitance, and see this and write down in your class book, and then we'll come up with the other two problems. So here is problem number 4 for today's half a dozen, and this is a very interesting problem. Just I did one problem before where we were talking about the induced charges within the inner plates of the capacitor, and you see it came in IIT 2001. That time it was IIT, now it is JEE Advanced. So you see the concept. Okay, in this problem you literally see that you need not to apply any formula, you have to just face the right concept to answer this question, and it came into IIT, in IITs. Okay, so they have given us, the problem is they have given us two capacitors, capital A and capital B. Please note it down. I am not showing you any picture, I am just telling you the sum. Please write down. This is the diagram. We have said that there are two capacitors, capital A and capital B, where A is charged with capital Q and B is uncharged. Okay, so what is the amount of charge B will store after this switch? Here is a switch, I'm sorry, I should mark it with S. The switch S is closed. You have to calculate the amount of charge B stores when the switch is closed, and A is stored with a charge of capital Q already. This is given. Okay, this is the problem. We have to calculate the amount of charge the B capacitor, which was initially uncharged, will store when the switch S is closed. Okay, so this is it. Can you imagine something out of it? Okay, when we derive the expression for parallel plate capacitor, you remember I had a connection of earthing to the outer plate of the capacitor. Okay, and I was even telling you while doing the problem just previously that it is the inner plate charges that matters for a capacitor, and so this capacitor A is having the inner plates arranged with this positive and negative charges. We have a strong electric field within. Okay, so when this switch is connected and this is uncharged, okay, then this capacitor doesn't have any charges which is stored outside the plates. You can see here there is no charge on the outside the plates. That means there is the charge which is inner charges staying within the inner plates, and they are strongly bound because of the electric field. They belong, which is equal to sigma by epsilon naught. The electric field here is sigma by epsilon naught if we consider the surface charge density for these plates to be sigma. Great. So if I even close this switch, since they are strongly bound, there will be no flow of charge. So B will have a charge which is equal to 0. So there will be no flow of charge since the plates are already having this binding energy, so that they can store the charges, held the charges due to their mutual induction, and they won't allow any charge to flow because we do not have any excess charge on the outer plates of the capacitor. This is the concept for this sum. There is no extra charge residing on the outer plates of the capacitor, and that is the reason why the capacitor B, even after the switch is closed, will contain zero amount of charge. There will be no charge flow. Okay, so you see, we didn't calculate anything. We just thought and answered the question. And the four options given were, there was one option which is 0, and there were some seven other options like q by 2, q by 3, q, and a lot of other options. Okay, so the correct option is 0, and it came in handy. You understood that how important the concepts are in order to solve the problem. The right concepts can only lead us to solving the problem only. Okay, now let us check the other problems coming up now.
Here comes an interesting concept. This doesn't belong to any problem, and I'm just showing you this concept because it will help us to do a lot of problems for entrance. You see, we have a network and we have capacitors connected, and we have terminal potentials for each of these endpoints A, B, and C. You can see at V2, V1, and V this way. So you have to calculate the potential at the junction O. For this particular figure that they want to know for both the figures. So if here we have to just understand one thing, that each of these capacitors, they do have a particular amount of charge, and then only this can be formed, as we can see. And so if the VO is the potential, then the charges on each capacitor of C1, C2, and C3 can be as followed as Q1, which is C1 into V1 minus V0. You see here is the difference, and then it is C2 into V2 minus V0, and the last one is V3 minus V0. In the diagram there are few abbreviations which are wrongly given. Hope you can understand the second diagram is better one, where you can correct that point C we should have a potential of V3, and similarly you please rewrite the charges. There are some mistakes in the diagram. Okay, and then we can apply the Kirchhoff's law, junction law. It is nothing, it's just an energy conservation. The total charge here should remain constant, so it's here that the total energy, there is no charge flow, so the total energy conversion is 0. So we can add up all these charges to get the total charge to be 0, which is Q1 plus Q2 plus Q3 equals to 0, which will give us an equation, and from here we can actually solve the common potential or V0. And you see this expression is very similar to that what we found in common potential concept. So here is another expression which is helpful for you. Do copy this with the rectifications given. So point A, and then that point the capacitor will be C1, B will be having a capacitor C2, and obviously the C point, O to C, this point will have a capacitance of C3, and respectively the charges will be Q1, Q2, and Q3, and even the potentials to be V1, V2, and V3 respectively. Okay, another concept is coming up right now. Please check that also and do copy in your classwork. This I told you while doing the normal class of capacitance for board, that is Western bridge. You see here, you know that these capacitors should be in a particular ratio, they should be in proportion. So then you can omit the middle capacitor because there will be no charge flow since the potentials are constant here. And I also did one problem in the capacitor video lesson. If you have skipped that, please watch it again, and then you can actually understand the problem based on these type of circuits which will be widely used for entrance. I'm repeat, this is very very important. I will explain you about Western bridge principle when I'll do with current, electricity, and the Kirchhoff's law portion. So right now just remember, if these capacitors in the upper half and the lower half they bear a constant ratio, then the intermediate or in between the capacitor which lies that C51 here in these three diagrams, that can be omitted or that can be removed, and then we can calculate the equivalent capacitance between among other capacitors which are thus connected. Okay, so this is the simple concept, you should know that. Now we'll do some problem based on the circuit problems. Let's check it out.
Now let us do a simple circuit-based problem so that we can understand how we can approach to the circuit. In the last phase of this half a dozen, I already had shown you a picture which was not a problem, which is not included within the dozen sums, but I gave you a concept which is important, applying Kirchhoff's law and the Western-based principles and all this. So now we can actually before winding up, we can do a few problems based on circuits so that we can understand how we can apply the concepts of solving circuits. Series, parallel combination is very important and it usually comes. And I'll do a lot of other problems when we'll do electricity, when we'll have resistance, this concept, just a few days later. Then we'll come up with another half a dozen where I'll include a lot of resistance and capacitance together to do the problems, and then that time it will be more interesting for you. But right now we are dealing with only capacitance. So here we have a circuit network. It came in one of the entrance, I don't remember the exact year, and I think it came in somewhere in NEET or JEE somewhere like that, but long back. But this is very conceptual in order to know how to approach to solve problems based on series parallel combination. They've asked us to find out the effective capacitance between AV. This is the question they've asked. So in order to find out the effective capacitance, we have to understand that we have to find out the effective capacitance between A and B. So here is the first junction from where everything is getting diverged. We have three branches. Okay. So first, if we go to this branch, then we can see that this two mu f, they are in series combination. So we can write this as series. I'll write only S from now onwards. So these two mu f's are in series. So effectively that is equal to 1. So if you can now understand that this one and this one, they are in parallel. So effectively 1 and this one, these two now, please understand, we have got this after solving these two in series, and now this capacitance and this value, they are in parallel. So the effective capacitance is now, this whole thing will be omitted, and we have only 3 capacitors. Now we have already resolved the branches. We can now redraw the circuit, and now this is the circuit now. Okay, this is A, this is B, and this is the rest of the circuit. And 1 and 1 parallel means it is 2, and this is 2, and this is 1. Okay, so here again you can see, if you just go for the whole thing, then these two, they are in series combination, and with that, when I connect A to B, I have one branch left, and I have another branch where these two are in series. Alright, so we have one branch like this. This is one branch, try to understand, and this is one branch. This is branch number 1, this is branch number 2. They are in parallel. 2 plus 2 series. This is series, and these two branches, they are in parallel. Okay, so 2 mu f, 2 mu f, what is the exact answer for series is again equal to 1 mu f. It is 1 mu f. Okay, so 1 mu f and this 1 mu f, they are in parallel. So what is, can you say the final answer? Let us write here 1 and 1, they are in parallel. This 1 mu f and this 1 mu f, they are in parallel. So the final answer is 2 mu f for this particular sum, and this sum is solved. Okay, so you can understand how simply we can actually apply the circuit diagrams to resolve the values for this kind of thing, and this is important. Okay, I'm telling you, in entrance, especially for NEET, these simple logic-based circuit solving problems, they usually comes. Even in JEE mains it comes. In the state level entrance examinations, like WebG and others, they also ask these kind of problems. So we have to understand how we can approach, and here formula is not important. It's important to identify the series parallel branches. Okay, wherever you see there is a continuous attempt, there is no other thing. Like this was a branch which has these two in series, and this was another branch, this was another branch. So these branch means parallel, continuous path means series. Just remember this, it will help you. And we have other network theorems that I'll discuss when I'll do resistance and capacitance together in another half a dozen some classes. Okay, now I'm almost in the winding up session. I'll be doing the next problem, and then we'll wind up this half a dozen involving capacitance.
So this is the last problem of half a dozen of capacitance today. Do copy this in your classwork, and you see that this came in Ep3 2008, which means JEE Mains 2008 actually. It's a very interesting one. It involves dielectrics and other concepts in parallel plate capacitor. So let us solve it now, and do copy it in your classwork, and right now see how we can solve it.
So you have already seen that it came in Ep3 2008, that is JEE Mains 2008, long back. But this is very interesting in order to gather the concept of capacitance. And here is the application of dielectric. Since I am going to wind up this section of half a dozen involving capacitance, so let us do a sum based on dielectric. So what they have given us, that there is a particular space of capacitor which is epsilon naught A by D, parallel plate capacitor which is equal to 9 picofarad, and there are two dielectrics of value k equals to 3 and k equals to 6. They are inserted with this kind of width, that is 1/3 is k1 equals to 3, and 2/3 is k2 equals to 6, and we have to find the effective value of the capacitance of this kind of arrangement, provided without dielectric they had a capacitance of 9 picofarad. Okay, first we have to understand this particular arrangement. You see, in this arrangement the total plate area is intact. Okay, we have inserted a dielectric so that we are getting the whole plate area as it is. So plates where the charges resides, even the induction that occurs due to the dielectric, that also resides within the inner plate of the capacitor. So it is obvious that we can understand that the charges after this kind of combination, the charges are same. And in which type of combination the charges remains constant? It is series. Okay, when we divide the plate area, if the same thing would have happened in this fashion, that means we were dividing the area, then it would have become a parallel combination. So we have a series combination here. We can understand this is a series combination having two capacitance, which is one having K3 and one having K6 with the width d by 3 and 2 d by 3. There are two capacitance here, and this is the expression for the series combination. That 1 by part I have taken above. So 1 by C dash is equal to 1 by C1 plus 1 by C2. So if I do the thing, then this C dash is equal to epsilon naught A by D, but here the D is different and even the dielectrics are different. So we write, remember this fashion, epsilon naught A will remain as it is. The d by 3 is the first width divided by the dielectric, second width divided by the dielectric. For the series combination, parallel is much more easy, we have to just add, it is not a big deal. But for series combination, we have to just manipulate so that in entrance we can do the calculation faster. Okay, so this is the expression. Now we know what is K1 and K2s are, so we can write C dash is equal to epsilon naught A by d by 3, and this is 3, so obviously this will become d by 9 plus 2d by 3, and this is 6, so it is again will come up to be d by 9 again. Okay, so finally we have a thing that is 4.5, because 9 by 2 will come into epsilon naught A by D, and this is 9 picofarad. So now your answer is very simple. It is 4.5 into 9, whatever the answer comes. You can understand that 4.5 into 9 will yield to a result which is nearing to 42.5 or something. So this will be your answer. 40.5 will be the final answer. You can understand. This is the final value for this kind of arrangement. You see here we have understood the concept that how dielectrics can actually be connected or inserted so that the whole combination becomes series or whole combination becomes parallel. This is very important for solving problems. We have to understand this concept. I am repeating again, when you are not dividing the plate area, you are definitely going for a series combination. And when you are dividing the plate areas, then keeping the width constant, then you are actually going for a parallel combination for the individual capacitances thus formed due to the varying dielectric within the here capacitor. Okay, this is the concept. This is what we have to remember. So here it is, the half a dozen for capacitance. We have done a lot of different types of problem in order to improve our concept so that we can actually deal with problems in entrance. I did problems from JEE Mains, JEE Advanced in the previous years, which are interesting. I'll do a lot of other problems because usually in entrance from these circuit problems, they involve capacitance as well as resistance, even some cases inductance. Inductance we haven't done yet, we'll do. So I'll do other problems based on half a dozen, based on only circuits. Later on, after I solve resistance, then I'll do a few problems for half a dozen involving resistance and capacitance together. That will be more interesting. Okay, so here it is. This is half a dozen for today, and we are winding up the class. So solve these problems. Sit back with the assignments that I'll send you for solving capacitance and other problems in electrostatics related to entrance. So do solve the problems. Those are there in the assignments that I'll send to you, and of course you should understand that this is a high time that you should stay safe and stay productive, so for the entrance in the next year 2021, and these are the few concepts that we should understand clearly. Okay, so this is it, and Rijit Ray, we have done the half a dozen with capacitance for today's session. Hope you have understood. Keep practicing, and I'll come up with a lot of assignments in our Accentus WhatsApp group. Okay, till then, bye bye.